Man, BME 147 or 247, microfluidics, it's like my favorite class.
Yeah, it gives me a lot of opportunities to work on different stuff, like the experiments and the projects. Like, it's cool, it's really good, don't you think so?
I'm so passionate about, oh.
Dude, can you see this? There are like different shapes of water droplets on this and this.
Yeah, man. What an incredible phenomena of microfluidics. We should probably do an experiment to check this out.
For our experiment, we will be testing the shape of different types of droplets placed on surfaces with different properties in order to observe whether or not the interaction between the droplet and the surface will maintain a compact shape for the droplet or cause the droplet to spread. Our hypothesis for the experiment is, if a droplet is placed on a hydrophobic surface, the droplet will be able to maintain a more compact shape than on the hydrophilic surface on which the droplet will spread.
The materials we will be utilizing in our project include water, Gatorade, and we will be dispensing these liquids with a plastic syringe onto a Teflon taped surface, and finally a glass surface. We will quantify our experimental findings by dropping 0.2 milliliters of water or Gatorade onto the glass and Teflon taped surface with the syringe in order to keep the volume of each droplet constant. We will record the droplet dispensing at a fixed distance and a fixed optical zoom, allowing us to compare the compactness of the different droplets. From enlarged screenshots of the droplets on a computer screen, which are kept at the same dimensions, we will measure the compactness of each droplet by measuring the diameter of the droplets with a ruler. From our experiment, we observed that both water and Gatorade are able to maintain a beaded shape on a hydrophobic Teflon tape, but spread out on a hydrophilic glass surface. This phenomenon can be explained by the surface chemistry of Teflon tape and glass. Because the Teflon tape has lower surface energy, it is more hydrophobic and repels both water and Gatorade, allowing the droplets to maintain a beaded shape. On the other hand, glass has a higher surface energy, making it more hydrophilic. Both the water and the Gatorade droplets are attracted to the glass surface, causing the droplets to spread out.
In a vacuum, a water droplet would be perfectly spherical. So why does that happen? Surface tension is responsible for the shape of liquid droplets. Although easily deformed, droplets of water tend to be pulled into a spherical shape by the cohesive forces of the surface layer. However, in the case of a hydrophilic surface, the droplet loses its spherical shape due to polar interactions between the droplet and the surface. Because the glass surface caused the droplet to randomly spread in all directions, we were not able to measure the diameter of those droplets.
Surprisingly, the Gatorade droplets were more compact in shape than the water droplets. This could be observed on a Teflon tape surface. The 0.2 milliliter water droplets had an average diameter of 6.75 centimeters when enlarged on a computer screen, and the 0.2 milliliter Gatorade droplet had an average diameter of 5.7 centimeters when enlarged to the same dimensions.
The compactness of the Gatorade droplet can be attributed to its higher concentration of the electrolytes and salts. Because the ion-dipole interactions of the molecules in the Gatorade droplet are stronger than the dipole-dipole interactions of the molecules in the water droplet, the Gatorade droplet's shell has stronger surface tension, keeping the droplet shape more compact.